Okay, in this example, we're given experimental data, and we have A reacting with B, and we're yielding C and D, and we are measuring the initial rate of reaction. And that word initial is just letting us know that we're mixing the reactants together, and as soon as they are mixed together, the reaction is going to happen, and we're measuring the rate of reaction right after the mixing. Because in reality, when we mix reactants together, they start to make products, and a lot of times products are going to react together to remake reactants. So then things get really complicated later on in the reaction. So if we limit it to just the initial part of the reaction, we avoid that confusion. Okay, so we have A plus B yielding C and D, and we want to write the rate law expression for this reaction. So they did not include the word differential in here, but they could have, and we will be talking about the same thing. So I'm going to write our generic equation. Our rate will be equal to baby K, your rate constant, times the concentration of reactant A raised to some unknown power, times the concentration of reactant B raised to some unknown power. Again, I do not use the coefficients from the balance equation. We are going to determine M and N, which we call our orders, experimentally. Okay, so I have to see how the concentration of A is affecting the rate, and then how the concentration of B is affecting the rate. We're going to show you two different methods. The first one is just going to examine this table, and we call this a table logic method. I'm looking for two experiments in which B is held constant, but A is changing. And I see here that experiment 2, B is 0.12, and it is also 0.12 in experiment 4. So I'm going to go ahead and highlight experiment 2 and experiment number 4, just to focus in our attention. So I'm keeping B the same, okay, but notice that the rate is changing. It's 2 and then it's 0.5. So why is that rate changing? If B is not changing, that must mean the rate is changing because I'm changing the other reactant A. So notice here in experiment number 2, the initial concentration of A, that's what that 0 means at time 0, it's 0.24 molar, and then experiment 4, it's 0.12. So I'm going to examine how the concentration of A has changed. Okay. From experiment 4 to experiment number 2, our amount of A has been doubled. And then I'm going to see how that has affected the rate of the reaction. It goes from 0.5 molarity per hour to 2, and that's 4 times. Okay, or the rate has been quadrupled. Okay, so as I doubled A, the rate has quadrupled. And so what does that M exponent have to be in order for doubling the amount of A is going to cause the rate to quadruple? If you remember back to our discussion about orders, we have 3 main types. We have 0, that has no effect on the rate. We have first order, which means it's directly proportional. If one doubles, the other doubles. And then we have second order, meaning if we have double our reactant, the rate is going to quadruple. And that's exactly what we see here in our example. Okay. The amount of A has doubled, causing the rate to quadruple. So therefore, the order for A is 2. So I would write the rate increases by a factor of 4 when the concentration of A is doubled and B is constant. Okay. Therefore, the reaction is second order with respect to A. Okay, so we're saying that A is second order, and this is just kind of the lingo that we use in chemistry to say that it's second order. We say second order with respect to A. Okay, now we're going to solve for the order of B in the same fashion. I want to see how changing the concentration of B affects the initial rate of reaction. So now I'm going to find two experiments in which A is being held constant, but B is changing. So I see here experiment number 1 and experiment number 2. A is remaining constant, but B is changing. So those are the two experiments I want to use. From experiment number 2 up to experiment number 1, the amount of B has been multiplied by 4. And then I examine how the rate has changed. It's gone from 2 to 8. That has increased by a factor of 4. So I've quadrupled B, and the rate was also quadrupled. So this means B is first order. So I would say the rate increases by a factor of 4 when the concentration of B is also increased by a factor of 4, and A is constant. It's important that you write that the A is constant, because that lets us know that A is not affecting the reaction rate. The reaction rate is solely being changed because B is being changed. Therefore, the reaction is first order with respect to B. So we call this method of looking at the data and seeing how quadrupling or doubling one reactant causes the rate to change. We call this method the table logic method. This is a very quick and easy way to just look at a data table and know what the order of a reactant is. This is particularly helpful on multiple choice questions. We're going to look at another way, which is called the mathy way, to more concisely determine the order of reactant by doing some division and to verify that these are in fact the reactant orders. But first of all, let's answer letter A. Write the rate law expression for this reaction. The rate law expression, or also called differential rate law, would be written as rate is equal to baby K times the concentration of A. But now I'm going to plug in the order for A because we determined that from our table logic. It has an exponent of 2 times the concentration of reactant B, and it has an order of 1. So technically, there is a 1 here, but we know we typically don't write 1s. Okay, for exponents, it's understood to be a 1. This is the answer for part A. This is your rate law, also known as your rate expression. Okay. Sometimes we throw in that word differential. All those mean the same thing. And the overall order of this reaction would be equal to the sum of the exponents, so 2 plus 1. So this reaction is third order overall.